Today, we're going to shrink all the way down to the microscopic level of atoms, and then zoom right back out to understand the macroscopic, real-world materials that literally make up the infrastructure of our modern lives. So grab your mental safety goggles because we are unlocking the secrets of metallic bonding.
I want to start our exploration with a pretty simple, everyday mystery. Just think about it for a second. Why can you sit at your desk and effortlessly bend a metal paperclip back and forth into all sorts of crazy shapes? But if you try that exact same bending motion with a piece of chalk, it just instantly and frustratingly snaps right in half. What invisible subatomic forces are actually at play here, giving these two really common items such drastically different physical properties? Well, our dive into microscopic science today is going to solve this exact puzzle.
Okay, let's dive into this. Here's our roadmap for today's explainer. First, the sea of electrons. Second, what makes metals strong? Third, everyday metallic properties. And finally, alloys, upgrading the metal.
Starting right off with Section 1, the sea of electrons and building the lattice. So before we can really understand how a massive steel bridge holds up tons of daily traffic, we have to look at its incredibly tiny subatomic architecture. Now, if you open up a standard chemistry textbook, you're going to see a definition somewhat like this. Metallic bonding is the electrostatic force of attraction between positive metal ions and delocalized electrons. And sure, while that is 100% scientifically accurate, it kind of sounds a bit dry, right? Electrostatic force, delocalized. Don't worry, I absolutely promise we're going to break down exactly what this actually looks like in practice because the reality is incredibly dynamic.
See those red circles with the plus signs? Right, those are our metal atoms. Now, what is really unique about metals is that they have a notoriously weak hold on their outermost electrons. Because of that, those outer electrons simply drift away from their parent atom. And since they've lost their negative electrons, the atoms are left with a positive charge, officially making them positive ions or cations. But those electrons that drifted away, they have nowhere else to go, so they form this incredibly fluid, constantly moving sea of electrons around a rigid, densely packed lattice of those positive ions. So, the absolute crucial point to take away here is this. The actual metallic bond is the magnetic-like attraction, that electrostatic force, between the rigid positive ions and the free-flowing negative sea of electrons, holding the whole shebang together like a sort of flexible glue.
Moving on to Section 2, what makes metals strong? Let's look at the rules of attraction.
Have you ever wondered why some metals are incredibly tough, like the tungsten they use in rocket nozzles, while others, like pure sodium, are actually so soft you can cut them with a butter knife? Well, it all comes down to three distinct subatomic rules of attraction that completely dictate the strength of a metallic bond. Number 1, the charge of the metal ion. Basically, how many protons are pulling from the center. Number 2, the number of delocalized electrons per atom. As in, how many electrons is each individual atom dropping into our fluid sea? And number 3, the size, or the radius, of the ion itself. The logic here is beautifully straightforward. A higher positive charge, a smaller ionic size, and a larger number of negatively charged electrons in the sea all add up to a much stronger electrostatic attraction. Basically, tighter glue means a tougher metal.
And this brilliantly illustrates that exact concept. Let's actually pit sodium against aluminum to see this in action. Sodium is a relatively large ion, and it only drops one single electron into the sea, leaving it with a mere 1+ charge. That attraction is super weak, which is exactly why it melts at just under 98 degrees Celsius. You could literally melt a chunk of it in a cup of hot tea. But look over at aluminum. It's a smaller ion, meaning its positively charged nucleus is way closer to the electrons, plus it drops 3 whole electrons into the sea, giving it a solid 3+ charge. More negative glue means a stronger positive pull. And because of this, it requires vastly more thermal energy to break those bonds apart, drastically raising its melting point to over 660 degrees Celsius.
Which brings us to Section 3, Everyday Metallic Properties, where we explain how form dictates function.
So how does this microscopic form actually dictate macroscopic function? Well, it totally solves our paperclip mystery from the beginning. When you apply force to a metal, like, say, bending a paperclip, the layers of positively charged ions in the lattice physically slide right over one another. But here is the absolute magic of it all. Because all the positive ions are identical, and because they're constantly bathed in that flexible sea of negative electrons, the attractive forces don't break when the layers shift. The ions literally just slide into a new position and settle back down. The metal bends, meaning it's malleable, without shattering. Our piece of chalk, on the other hand, that relies on alternating positive and negative rigid bonds. If you try to slide a layer of chalk, positive aligns with positive, they powerfully repel each other and snap. The chalk breaks in half.
But malleability isn't the only superpower metals have, not by a long shot. They're also world famous for being excellent conductors of electricity and heat. And once again, we have our trusty sea of electrons to thank for this. Those wandering, delocalized electrons are basically the perfect tiny messengers. Because they aren't tethered down to any single atom, they're completely free to move around. Think about it. If you heat up a frying pan, those free electrons rapidly transfer the kinetic thermal energy right through the solid structure to cook your food. Or if you apply a voltage, those exact same electrons flow in a uniform direction, carrying an electrical current across a copper wire to power your entire home. It's pretty amazing.
And that leads us into our final section, Part 4, Alloys, Upgrading the Metal and Engineering Better Materials.
Okay, so we understand natural metals now, but we humans, we're tinkerers, right? We actually figured out a really clever hack to manipulate these microscopic structures to completely upgrade their macroscopic properties. Welcome to the fascinating world of alloys. Simply put, an alloy is just a mixture of a primary metal with other elements, and we do this specifically to make the base metal harder, stronger, or maybe more resilient to its environment. Pure iron, for instance, actually rusts surprisingly easily and really isn't as tough as you might think. But if you mix in some chromium and nickel, bam, you get stainless steel, a remarkably hard, corrosion-resistant alloy that we use in everything from surgical scalpels to towering skyscrapers. Another great example we pulled from the sources is duralumin, which is a mix of aluminum and copper that is absolutely vital for the aerospace industry.
Now, what's really interesting about this is exactly how alloying achieves this massive upgrade. What you're looking at is a lattice of magnesium, which is an alloy of aluminum and magnesium. Remember how pure metals bend because their identical, perfectly uniform layers so easily slide over one another? Well, when you introduce a different element, you are introducing atoms of a completely different size into that nice, neat lattice. Just look at those larger magnesium atoms. They physically disrupt the regular pattern. They essentially jam up the lattice layers, completely preventing them from sliding smoothly when any sort of pressure is applied. And because those layers can no longer slide, the resulting alloy ends up being significantly harder and way more rigid than the pure metal it started out as. It's an incredibly simple but absolutely brilliant microscopic trick.
From a sea of free-flowing electrons that allow metals to gracefully bend and conduct electricity, all the way to the precise size of atoms that determine an alloy's incredible bridge-building strength, it's just amazing to see how the microscopic world dictates our macroscopic reality. But, materials science is far from a finished book. We are constantly out there experimenting with new mixtures and molecular structures. So I want to leave you with this final thought to ponder today. If simply mixing different-sized atoms into a lattice changes everything, what ultimate, seemingly impossible metal alloy is just waiting to be discovered by the next generation of scientists? Thank you so much for exploring the secrets of metallic bonding with me on today's Explainer. Keep learning, keep questioning, and I'll see you on the next one.